Now we've started doing some simple programming in Ask, but we can't do anything very interesting yet because we have nothing that looks like looping. If we look at a data type like nat, this is a recursive data type, meaning that it refers to itself in its definition. A natural number is either 0 or it's the successor of another natural number. When we have recursive data types, what we really need is recursive functions, which are allowed to refer to themselves in their own definition. An example of the sort of function we'd like to be able to write is addition of natural numbers. I can write its type signature in Ask in two different ways. Either I can write plus in brackets and then a double colon and then nat, arrows, nat, arrows, nat. This is how I say that this is a function with two inputs. So plus takes a nat and it returns a nat. Alternatively, I can write it like this. If I have a natural number a plus a natural number b, then the result is a natural number. So Ask will accept either of these two styles and they mean exactly the same thing. The first one looks basically identical to how you would write it in Haskell. The second one looks a bit closer to how you would write it in a language like Java if you rearrange it a bit. Anyway, we only need one of these two, so I'm going to comment out the first one. Okay, now I'm going to write define a plus b with a question mark. So this is the initial state of our question, that how do we define a plus b? Now I'm going to use a new keyword. I'm going to write inductively a. When I send this to Ask, it looks like nothing has changed because it's still asking me to define a plus b. But secretly, after writing inductively a, I've gained a new ability because now I can refer to plus in its own definition. This superpower comes with an important restriction, which is that the a input has to get smaller every time. So if I had instead written inductively b, then it would be b that would have to get smaller. Okay, so the next thing that I want to do is to inspect one of the inputs. I'm going to inspect the a input, so I'm going to write from a. Now, Ask tells me that a is either 0 or it is the successor of some natural number called n. Okay, so we can deal with these two cases in turn. So what is 0 plus b? Well, we don't need to inspect what sort of thing b is because we know that 0 plus b is always b. So in this case, I can just write equals b and then we're done. Okay, and in this case, okay, let's think about this. Suck n is really meaning n plus 1. So what is n plus 1 plus b? Well, it's the same thing as n plus b plus 1, which is also known as the successor of n plus b. So what I'm going to do is I'm going to write equals suck n plus b. So here is where I'm using plus inside its own definition, but I'm allowed to do that because n is smaller than a. And this is a complete definition of plus now. Ask also gives us a keyword to run the functions that we've defined. The keyword for that is test. So I can compute 2 plus 2 by writing test and then suck 0 for 2 plus suck 0. And then reassuringly, the thing that Ask sends back contains suck 4 times. So it has successfully computed that 2 plus 2 is 4. The keyword test has a double meaning. I can use it to essentially play with or try a definition which I've given. So this is like taking a car for a test drive, but I can also use it in the software engineering sense to write a test. So I can say this, and for example, let's say I was confused and I thought that 2 plus 2 was 5, then I could do this. And this should now be a failing test. And Ask will tell me that, in fact, 2 plus 2 is 4 and not 5. So this is what a failing test looks like. Okay, here's another example which is quite similar, concatenation of two lists. that is joining two lists end to end. So its type looks like this. It takes two lists and it returns a list. Now I'm going to write define concat A's, B's. So I'm going to call my two inputs A's and B's. It's traditional that inputs which are lists are given a name like this. And then I'm going to write inductively A's and send this. Okay, so now I'm going to do pattern matching on the first list. So I'm going to write from A's. And now ask tells me that the first list is either empty or it's a head element joined onto a tail list. Okay, so we can deal with these two cases in turn. How do we join the empty list onto the front of a list B's? Well, that's just B's. Okay, the second case is a lot more interesting. Okay, so the first list looks like a head joined onto a tail, and then we have to concatenate that with a list B's. So what we can do is we can concatenate tail with B's, and that gives us the answer, but with the head element missing, and then I can cons that back on. So I can write equals concat tail B's, and then cons head of that. And that is how I define concatenation of two lists. Okay, maybe this looks a bit mysterious. The style of programming using recursion is very different to what you do in a programming language like Java. What I can say from experience is that programming like this basically takes practice, and it gets much easier with practice. And eventually you will be able to write this kind of thing with barely thinking. Okay, let's do one more example before you start trying to do this kind of thing yourself in the exercises. Let's write the data type of node labeled binary trees from the first exploration this week. So data tree A is leaf or a node with a left subtree and a value of type A and a right subtree. Okay, let's write the function which flattens a tree into a list. So it should turn a tree into a list that contains the same data values and in the same order. Okay, how do we do this? So its function, flatten, is a function from tree A to list A. And I'm going to write define flatten x inductively x. Send that. And then I'm going to write from x. And ask tells me that there are two cases. Either my input is a leaf or it's a node. And if it's a node, then I'm given a left subtree, a value, and a right subtree. Okay, so the first case is easy. If my tree is a list, then it contains no data values. So in order to flatten it into a list, it's just the empty list, which is the list that contains no data values. So here I can write equals empty for that case. Now, the second one is a bit harder, but what we can do is we can use something that we've defined earlier, namely how to concatenate two lists. So if I have a tree, think of a tree like this. How do I flatten it? Well, I can flatten the left subtree, and then I can flatten the right subtree, and then I can join those two lists end to end. It's not quite as simple as that because I also have this data value which needs to go somewhere in the middle. So what I can do is I can, so this data value, I can cons it because I can use cons to join something onto the front of a list. So if I join it onto the front of the right-hand list, then that's the same as putting it in the middle. So I can say concat flatten left, cons val flatten right. And there's my definition. Okay. That's the last exploration for week 3. So now it's your turn to go and try the exercises where you'll be defining data types and writing recursive functions. And then next week, we're going to start proving things about our programs.